Good evening. Please tell me, am I audible? Am I audible? Please tell me, am I audible? Good evening, Shashwata. Please tell me, Shashwata, am I audible? Am I audible, Shashwata? Yes, thank you. Thank you. So, today I am going to discuss regression analysis. Sharnabu, yes, Sharnabu, thank you. Rinit, good evening. I think this is your first class, Rinit Podjo. This is your first class. Thank you. So regression analysis, by regression, actually, first I define this, then we're going to discuss. By regression, of a variable y, sometimes it's called study variable. It's called study variable or Shai, good evening. Study variable or response variable. Or dependent variable. Or another variable, x. We generally call x as a independent variable. Okay, Shashwato, that's why I'm okay. Okay. Now it is clear. Now it is clear. Now it is clear, Shashwato. Now it is clear, Shashwato. Now it is clear. Please tell me now, is it clear or not? Yes, okay. So on another variable x, which is called independent variable, still not audible. Okay. Now it is fine, Shashwato. Hello, check. Hello. Please tell me. Now audio. Okay, thank you. So another variable x, which is called independent variable or explanatory variable, or regressions. we mean the dependence of y on x on the average. In bivariate analysis, one of the major problems is prediction of the value of the dependent variable y when the value of the independent variable x is known. The problem becomes simplified if we can express y as a function of x, that is, say y equal to 8x. Then the equation this equation is called the regression equation of y on x. In the simplest case, when y is linearly related with x, either exactly or approximately, we can write y equal to a plus bx, so that a plus bx naught is the predicted value of y when x is equal to x naught. And here we confine our discussion to the linear regression only. Okay, so we just restrict our discussion on linear regression. Linear regression, that is y equal to a plus bx. Sometime, actually, sometime y is not possible. Y is not available. For example, due to this pandemic, most of the boards and university did not take their final exam. In that situation, if you have a uh, internal marks, then you consider these internal marks as a x and use this regression, you can predict final exam, final marks of a student. So in that way, if you use this regression equation, actually for this, if you need not only you have a previous knowledge about use this, you can use before using this regression, you need a set of observation, and using this set of observation, you can use this by using this regression and using internal marks, you can predict the final marks. So sometimes it is not possible to predict y, and using x, sometimes it is not possible to get exact value of y. In that situation, you can use regression analysis to predict y using the given values of x. For example, weight of a bear, it is not possible to take the weight of a bear because it is dangerous sometimes. So in that situation, if you know the other parameters of a bear like height, so you can easily predict the weight of a bear. In this type of situation, you can use regression equation, okay, to predict the future data or any value which is missing. This value you can easily estimate by using regression analysis. Okay, so this is the utility of this or advantage of this regression analysis. Okay, so this A and A and B both lies between minus infinity to plus infinity. That is AB belonging to real number. So you can choose any value A and B from this set and you get y. But thing is that we do not know this regression is this prediction is good or bad. So in that situation, you need to find error. Suppose this is the first observation and y1 hat is the prediction of this. Suppose we have a set of n observations xi, yi, I from 1 to n, and this is the error term. I denote this by E1 for the first observation. For the second observation, we denote this error term by E2 and so on. So, but thing is that if you draw the scatter plot, for example, suppose so every time for every choice of A, B, you get a different state line, and every state line you have a prediction for each pair, each corresponding each xi. Okay, I think it is better to illustrate with an example. That will help you. Suppose I have a set of observations. So the thing I use is a set of observations. Please wait. Okay. Okay. Fine. So I think x is equal to 10, 20, better. Okay, fine. Suppose, so please see the diagram, okay? Only 4 points. This is correspond to, this point correspond to x1, y1. This correspond to x2, y2. Better. This, 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 this. Okay. So this is x1. I denote this by capital A1. Okay. A1, where A1 is x1, y1. This is A2, which is x2, y2. This is A3, x3, y3. A4, x4, y4. Okay. So for any choice of AB, suppose for particular choice of AB, you get this straight line. Okay. So for this straight line, so this is your x1. Okay. This is your x2. This is your x3. This is your x4. Clear? So now see that this is this is the this is red color. I think I did not use different color for this. This is your x4 y4 hat. Okay. So and the error is, this is the error. This is the error because this one is x4 y4. So error is y4 minus y4 hat. Okay. Similarly, this is x3 y3 hat and this one is x3 y3. So error part is y3 minus y3 hat. and this one y2 minus y2 hat, and this one is y1 minus y1 hat. So these are the errors. If you use this straight line, these errors are occurred. Okay, and if you use another straight line, I use different color for this, say this, then you see that for this point, for x4, if you use this straight line, blue straight line, then the error is smaller than the if you use the previous straight line. Okay, because this the length of, I denote this by x4 y4 hat star. Okay, now y4 minus y4 hat star is less than y4 minus y4 hat. Again, you see this is the y3 minus y3 hat star, which is again less than y3 minus y3 hat, and here if you use this straight line, then you see that again this error is smaller than y2 minus y2 hat less than y2 hat star. Similarly, if you use this straight line, again you see that the error here also, the error is smaller than previous. Okay, so in that situation we can easily see that if you use green straight line, then error is overall error is minimum than previous straight line. So if you compare these two straight line, I think my suggestion is you should use green straight line. This is better, give you better estimate than previous one. But it is, you can easily visualize this thing because the number of points is small, that is 4. But look at the another graph. So you see that so if you compare these two, you see that this error is minimum for this straight line, then I denote this by straight line 1 and this is straight line 2. So this error, if you use this straight line 2, then the error is minimum for straight line 2 and error is minimum if you use this, error is minimum for regression equation 1 than regression equation 2. Okay, similarly if you use straight line 2, then this error is minimum than regression equation 1. Similarly, this error is minimum for regression equation 2, but this error is minimum for regression equation 1 than regression equation 2. So here we get a misleading things. Okay, So some error is minimum for straight line 1, some error is minimum for straight line 2. So uh, uh, this is not the appropriate way to minimize to give a or choose a best regression equation. So for this reason, it is one you can use one of the criteria, that is, if you add all the error, that is summation ei, suppose there are n errors, okay, for all the straight line, all possible choice of all, that means you take a all possible choice of A and B in R real line, and you have a such number of straight line for every state choice of A and B. You compute, you can easily compute yi equal to a plus bxi, and for every choice of AB you get a error ei, which defined as yi minus yi hat. So that is yi minus a plus bxi. Sometimes it is called, okay. Yes, no, actually y hat is a estimated value. Estimated value of y, okay, for given x. For example, suppose your x is 8 and y is something 10, and you predict y hat for given values of 8, then this y hat is not 10, it should be a plus 8b, and the difference is y minus y hat, which is called error or residual, corresponding x is equal to 8. Okay, Shashwat, please tell me, if you need more explanation, I have no problem. So take your time and tell me, can I repeat this thing again? If you have any doubt, please tell me. I think can I repeat this again? I have no problem. Please tell me. Okay, I think I can. Yes, yes. Thank you. Okay. So please listen carefully. I am going very slowly. Okay. Our aim. What is our aim? To choose best regression line. Okay, this is our goal. From the set is from this set. Okay. Suppose we have n observations. We have n observations xi, yi. we have n observation xi, yi. So we want to choose best regression equation from this set. So best means what? This is a true value of, because we want to predict y. So true value of y minus predicted value of y. This gives you error or residual. That is, this is x, because you construct regression line based on this n pair of observations, x and y, x1, y1, x2, y2, x3, y3, xn, yn, and for given, you choose one pair from this set A, S, say A star, B star. For this particular A star and B star, you compute A hat, Y hat, which is the predicted value of Y. So this is A star plus B star x1, which give y1 hat, A star B star x2, y2 hat, A star B star x3, y3 hat, A star B star xn, yn hat, so on. So this is the predicted values. So in that way you can compute residual. I denote this by E or error. So this is y1 minus y1 hat, this gives you e1, y2 minus y2 hat, this gives you y2, y3 minus y3 hat, this gives you e3, yn minus yn hat, this gives you en. Now I change this notation for this set A star B star. To get predicted value y hat, I denote this by y hat star. Okay, so this is y1 hat star, y2 hat star, y3 hat star, yn hat star. So please tell me, up to that clear or not? Shayok Shashwat, yes or no? Shayok Shashwat, please tell me, up to that clear or not? Okay, thank you. Next, for another set of A star B star, we get similar type of tables. I denote this by y double star, and I denote this residual for A star B star by E star, and this is E double star. Okay, similarly, all possible A B we get infinite number of y hat star. Actually, for every choice we construct y, we predict y hat, or actually I want to say for different choice of A, B, we can construct such type of table, and since this is a infinite, the dimension of S is infinite, so we have infinite number of such predictions. Up to that clear or not? Tell me. Please tell me. Tayo, Tornabo, please tell me. Uh, are you agree with my statement that we can get an infinite number of such tables? Shayok, simple things. Because A, B belonging to R, you have infinite, because yes, sir. How are you getting this A star, B star? Actually, at that moment, we have a free choice. Actually, any elements in this set is a choice of A star, B star. Okay, choice of A, B. Actually, this is a S is equal to Cartesian product R cross R. So you can choose 1, 2, 1.5, 2.5, any number which belonging to real number. So because you actually y is a linear function of a plus b xi. So a b belonging to minus infinity plus infinity, you give any value, any real value of a b. Okay, so that's why I'm telling you can get infinite number of regression line. Yes and no. Shayo? S belong because see S is equal to the set, the collection of AB such that minus infinity A lies between plus infinity. Okay. B also lies between minus infinity to plus infinity. So that means, for example, suppose S belonging to AB, A only take 1 comma 2, B only 1 comma 2. Then this means A is a 1 comma 2, 1 comma 1, 1 comma 2. This is called Cartesian product. Okay, 1 comma 2, 2 comma 1, 2 comma 2. In that case, S contain only 4 elements. So in here, S contain infinite number element. That means in two-dimensional space, S represents any point in a two-dimensional space. Any point or point in a two-dimensional space. Yes and no, right? Please respond. If you choose any point from two-dimensional points space and use this point to construct to construct the regression equation, because we give a linear equation of y is a linear function of x, so you need to choose just slope and intercept. Okay, just slope and intercept. So and slope and intercept both are belonging to real line, so you can choose any value from this real line and use this two value, you get y equal to a plus bx. Okay, so in that way you get an infinite number of regression line, and thing is that, and every times you get a residuals or error, and sometimes some errors are smaller than other lines and some are larger than other lines. So if you just using compare the errors of every state lines in that uh, this is not the appropriate way to choose best regression line, because some errors are smaller, some errors are larger. It is not possible to compare this regression line just looking at the individual error terms. So we need a criteria. Why just give just look at this diagram, you can easily see that. That's why I use this diagram. Okay, so if you look at this diagram, so this is the points. So if you use this straight line and this straight line, you see that this straight line is closer to this point, but this straight line is closer to this point. So it is not possible just look at the individual error. Okay, and since our error is parallel to y-axis, because I defined E equal to y minus y hat, this means this is parallel to y-axis, so that's the error should be this perpendicular line. So individual error, if you just look at the individual error and compare these errors, so sometimes this line is better for this error, but for these observations, this line is not better. This line is better. So individual error, just looking at the individual error does not give a clear picture to choose a best regression line. So that's why we need a criteria which gives a best regression equation. So in that situation, we use the criteria which minimize sum of square due to error. So because we have a n number of observations, xi, yi, I from 1 to n, and this is the error term. I denote this error by delta, sum of square due to error by delta, and the criteria is minimize this error with respect to A and B, and this is called least square technique. Okay, please tell me if you have any problem. Please tell me. So thank you, sir. Okay. So next point is derivation of linear regression equation. Let the linear regression equation of y on x is a plus bx. I denote this by 1 since we would like to use this equation for prediction purpose. The constants a and b have to be estimated on the basis of observed values of x and y. Suppose we are given n pairs of values xi, yi, I from 1 to n of x and y from among different methods that are available for determining for the determination of a and b. We use here the method of least squares. Okay, actually these least square methods or least square technique, you do not need the distributional assumptions. Okay, you may sometime if you know the distribution of y and x, then you can use likelihood method. Actually this is not for your standard. When you third year or sixth sem, I think sixth sem or master degree level, then you know this thing. Okay, at that moment we just restrict one method, that is least square technique. This is the easiest one because in that case we do not need any distributional assumptions for estimating a and b. And least square methods, the philosophy of least square method uh, is that actually this is minimize the total sum of square due to error. Actually it is minimize the total sum of square, actually sum of square due to error with respect to constant a and b. So when x is equal to xi, the observed value of y is yi, and the predicted value of y is a plus bxi. So ei, which is equal to yi minus a plus bxi, is the error in taking a plus bxi for yi. This is called error of estimation. The method of least square requires that AB should be so determined that sum over I from 1 to n, ei square equal to I from 1 to n, yi minus a minus bxi whole square is minimum with respect to a and b. Please note that this is not only the method, it is one of the methods for finding linear regression equation. That's why this is called least square linear regression equation. For using, note that using least square regression equations, sometimes it's called least square regression equation, because here we apply, apply least square technique to find this regression equation. That's why this is sometimes called least square regression equation. Okay. So determining ai square I from 1 to n, I yi minus a minus bxi whole square is minimum with respect to a and b. Again, I am telling you this is not only method, this is one of the method. Least square is one of the method to find best, best or it is better to set a good linear regression equation. Okay, because statistics very much depending on data. Okay, sometimes least square gives a better result, but sometimes it may not be. Okay, so that's why I am saying this is one of the good or one of the good technique to find least square, find a regression equation. This is one of them, not only. So the others method you learn, uh, you will learn in either in uh, next semester or in master degree level. Okay, so the equation for the determination of A and B are this is equal to 0. Partial derivative, this is called partial derivative with respect to A, and this is partial derivative with respect to B. And from this we get sum over I from 1 to n yi minus a minus bxi minus 2 into sum over I from 1 to n yi minus a bxi. This is partial derivative is a simple derivative, but in the differences, in that case, we consider here b is a constant. Okay, the same thing, ordinary derivative, the method of ordinary, we use same method of ordinary derivative, but the difference is b is constant and here a is constant. Zero equal to 0. Okay, so or sum over yi equal to na plus b sum over xi. I denote this by equation number Roman 1, and from here we get sum over xi yi I from 1 to small n a sum over xi I from 1 to small n plus b sum over xi square. I denote this by Roman 2. Sometimes this is called normal equation. Okay, this is called normal equations. This is called normal equation. And the normal equations are sum over I from 1 to n yi n plus b sum over xi I from 1 to n and I from 1 to n xi yi a sum over I from 1 to n xi b sum over I from 1 to n xi square. I denote this by 2. Now from 1 a hat or is a equal to y bar minus b x bar, where y hat equal to 1 by n sum over yi I from 1 to n xi x bar equal to 1 by n sum over I from 1 to n xi. Sometimes we denote this by a hat. which is the estimate of A. Because A is unknown, we estimate A using n pair observation xi, yi. So it is better to say A hat instead of A, which is equal to y bar, and it should be B hat because B is unknown. We estimate B using xi, yi, that is x bar. So A hat equal to y bar minus B hat x bar. I denote this by 3. From 2 and 3, I from 1 to n, xi, yi, A is y hat minus b hat x bar, sum over xi, I from 1 to n, plus b I from 1 to n, xi square. And this should be b hat because I use, this is because I use b hat here, so this should be b hat. Okay, so now this is n y bar b hat x bar because summation I from 1 to n xi equal to n x bar, so I write n x bar instead of I sum over I from 1 to n xi. This is equal to b hat sum over I from 1 to n xi square, or sum over I from 1 to n xi yi minus n x bar y bar, which is equal to b hat sum over I from 1 to n xi square minus n x bar square. Or this is equal to sxy b hat sxx, where sxy, which is equal to sum over I from 1 to n xi minus x bar yi minus y bar, which is equal to I from 1 to n xi yi minus n x bar y bar. Just using simple algebra, we get this thing. Please check. Similarly, sxx, which is equal to I from 1 to n xi minus x bar whole square, equal to I from 1 to n xi square minus n x bar square. So variance of x, this is equal to 1 by n sxx, covariance of xy, which is equal to 1 by n sxy. So therefore, b hat equal to sxy by sxx, which is equal to covariance of xy by variance of x. Or we know covariance of xy is nothing but a r. R is a correlation coefficient between x and y by sx, sy. Sx is a standard deviation of x, sy is a standard deviation of y by sx square, then r into sxx by sy sx, where r is a correlation coefficient of x and y. So which is equal to covariance of xy by root over variance of x, variance of y, which is equal to sxy by sx sy. Okay, so therefore regression line of y on x is y hat. We use y hat for predicted value of y equal to a. A is our y bar minus b hat x bar plus b hat x bar. So sorry, b hat x then y hat y bar plus b hat x minus x bar. So y hat equal to y bar plus r into sy sx x minus x bar. So this is the regression equation of y on x. So just I recap all these things one by one. Please tell me, please first you tell me, have you any problem? So any doubt, please tell me. Shayok Shashwat, please tell me if you have any doubt. Please let me know. Tell me. Shashwat, Shayok, are you hear me? No doubt, sir. Thank you. So we start with the problem. The objective is, this is the flow chart actually. So the problem is we have infinite number of regression line y equal to a plus bx. Why? Because for every choice of AB, for all choice of AB, it's better to say in that way, for every choice of AB which belonging to R squared, we have y equal to b, a plus bx, and so the problem is choose or give a criteria or method to choose best, one of the best regression line in the sense of prediction. Okay, so for this we see that looking at the individual error is not a good procedure. So we use, instead of using observing individual error, we observe, we compute sum over ei square for every regression line, all possible regression line, and choose the regression line which minimize, choose the regression line, we compute this for all regression equation. That means for all regression, for the regression equation regression line for all possible choice of for all possible choice of for all possible choices of AB belonging to R square, and choose regression line which has minimum EI square. Okay, so this is the method. First is, we have infinite number of regression line. Looking at individual error is not a good procedure. It is very difficult to uh, find out best regression line just looking at individual error component. So for this reason, we compute we use this criteria, that is sum of error sum of squares. Error sum of square, we compute error sum of square for all regression lines, and then we select the regression line which has minimum error sum of square, and this method is called least quantity. Okay, so please tell me, have you any problem? Can I wrap this portion? Can I wrap the left side part? Shashwat, Suman, please tell me, can I wrap the left side? Okay, thank you. Sorry. Similarly, so the quantity, so quantity SYXX is called the regression coefficient of Y on X, and it is denoted by capital denoted by beta yx. Okay. It interpreted as it gives the increment in y for a unit increase in x. Note, this is not a this may not be this may not be unitary. Okay, because this is unitary only when x and y have same unit, otherwise not. It may be noted that there is another regression line the regression line of y sorry regression line of x, not y, regression line of x on y. So here x is a dependent variable or in study variable or response variable, and y treated as independent variable, study variable, this explanatory variable, and regressor. Okay. So and to obtain and to use this for predicting x from y, to obtain this line, we may write x is equal to c plus dy and use same procedure as above. This is your homework. We get c hat equal to x bar minus d hat y bar and d hat equal to sxy by syy, where this is equal to covariance of xy by variance of y equal to r into s x by sy. So this is your homework. Please do it yourself and submit. Otherwise, you may penalized, because you know there is a internal marking. internal marks. Okay, so please submit your homework time by time, otherwise you may be penalized for this. Okay, so the equation of x on y is x is equal to x bar plus r into sx by sy into y minus y bar. Okay. The quantity r into sx by sy usually denote denoted by beta xy is called regression coefficient regression coefficient of x on y. I think it is better to write small b instead of beta. Okay, please change the notation. Please change the notation. Instead of beta, please write bxy. Here also you change this notation byx. Okay, it's better to write b. So, and it means an interpretation of this bxy it gives the you can mail me or please wait, I will provide you the Google link and you can submit via this link. Okay, either you mail me or you can submit this via this mail via this link. So my mail address is Dr. Ganesh DUTTAGANESH 78 @gmail.com. Okay, just mail me this address. Okay, can I repeat this again? Is it visible? Dr. Ganesh DUTTA Dr. GANESH 78 @gmail.com. So interpretation it gives the increment in x for a unit increase in y. Okay, some remark. if you look at these two regression lines, then you see that the two regression line intersect at x bar y bar, as can be seen from the fact that both the equations are satisfied by x is equal to x bar and y equal to y bar. Next remark, two regression lines are usually different because they are derived under different conditions. Why? Because if you look at the diagram, so if you consider regression line of y on x and the error, and suppose this is the regression line, red color, and see that this perpendicular line because for regression equation of y on x, we already mentioned that the error should be parallel to y-axis because this is y minus y hat also function of y, function of x. So this should be parallel to y-axis. This gives error. And for regression line, y on x, this is regression line of x on y, sorry, x on y, and error. This error is parallel to horizontal axis. Okay. So the error is parallel to horizontal axis. So for finding this least square regression y1x, we minimize the sum of square where the errors is where the errors are parallel to y-axis, and for finding the regression line of x on y, we minimize the error sum of square where errors are parallel to horizontal axis. So this is the we use two different conditions to find two different regression lines, because one is parallel to errors are parallel to y-axis and another is parallel to x-axis. So these are the two different conditions for finding two regression line y1x and x1y. So that is why these two regression lines are not same. So we can write this thing in getting the regression line of y1x, we minimize the sum of squares of the errors of estimation of y while for the other we minimize error of estimation of y, while for other we minimize the sum of square errors of estimation of x. Geometrically, in the case of the former, that is regression equation of y on x, we minimize the sum of squares of the vertical distances of the observed points from the regression line, and in the case of the latter, that is regression equation of x on y, we minimize the sum of squares of the horizontal distances of the observed point from the regression line. Okay. The two lines, however, coincide when r equal to plus minus 1. That is, when the relation between when the relation between two variables when the relation between the two variables is exactly linear. Okay, so I want to stop today. So next day we will discuss the property of regression coefficient, and we will discuss the properties of regression coefficient. Okay, and and if possible we do some problem based on the regression analysis. Okay, and one thing I will tell you, I will start a quiz before starting the main class, that is the 5 or 10 minutes quiz. You will see the question on screen and answer uh, via comment section. You can answer you answer this via comment section. Comments, write a comment on the comment section. Okay, and every from I think this will be continued. Okay, every every class starting before every class there is a 5 or 10 minutes quiz based on the class which already completed. So please uh, be prepared. Okay. So based on your answer, uh, I I will assist you, and I will give a marks, internal marks on that, not only homework, also on the based on this quiz. Okay. So please tell me, have you any problems or difficulties regarding this topic? Otherwise, I I end the stream. Yes, yes, Shashwat. This is your homework. And one thing I repeat, uh, I will start a quiz based on the topic which I already uh, taught. Okay, so that means just previous day or day before. That means, for example, the next day, the quiz based on regression analysis and correlation coefficient. Okay, so this is a 10 minutes, 5 to 10 minutes quiz. Uh, I give you you can see the on screen, the question on screen and answer. You answer this via command section. Okay, so I I not only assist you via homework, I also assist via this quiz also. Okay, so please prepare. So your homework is not only you also solve you also submit the you need to submit the homework of previous class also. Okay, and today I give you only one homework, that is find the regression equation of x on y. Okay, so please submit this homework using to my and send after completing your homework. Please send me via my mail. Okay, so please tell me, have you any queries or question? Otherwise, I end this stream. Please tell me. Okay, thank you. So, Shash, have you any question? Please tell me. Okay, sir, if you are giving a line y equal to a plus bx, how to understand whether it is y on x or x on y? Okay, Shashwata, actually, I'm telling you, suppose if you have a line y equal to a plus bx, okay, so we can consider this line as a regression equation of y on x or regression equation of x on y. Okay, this is one of these, either regression equation of y on x or regression equation of x on y. So if y equal to a plus bx, sorry, if y equal to a plus bx is a regression equation line of y on x, then b is your regression coefficient of y on x. If y equal to bx is a regression line of x on y, then you can write y equal to a plus bx as okay. So regression coefficient of x on y is 1 by b. So now check if it is a regression equation of y on x. You see the property bxy byx. This should be r square. Okay. So now you can use this thing. You can say that which one is a regression equation of y on x. Is it a regression equation of y on x or x on y? Okay. So yes or no? Please tell me. Do you understand or not? শাশ্বত? So okay, because if this product byx bxy greater than 1, which is not, that means your assumptions is wrong, because this is not a regression equation of y on x, because your, because since bxy and byx is a r square, that means r square should be lies between 0 to 1, and bxy and byx, this product, if it is greater than 1, so your assumption is regression equation of y on x. This is not a regression equation of y on x, hence it is a regression equation of x on y. In that way, you can argue that. Okay. So I give you the example, numerical example, that will help you. Okay. Shashwat, please wait. According to, suppose we have a two regression line, x plus 2y minus 5 equal to 0. And another regression line is 2x plus 3y minus 8 equal to 0. So now the problem is, which one is the regression line of x on y? So Shashwat, your question is not correct. Okay. So that's why the question should like, question should be like that. Okay. You have a two equations. Which one is regression equation of all x on y? Process is same. This is the process. So first, you assume that x plus 2y minus 5 equal to 0 is a regression equation of y on x. So we write this as, so regression coefficient of y on x should be minus 1. Similarly, since we assume that x plus 2y minus 5 equal to 0 is a regression equation of y on x, so this should be regression equation of x or y. So this is equal to 8 by 2 plus 3 by 2 y. So minus 3 by 2 y. So this is the regression coefficient of x on y equal to minus 3 by 2. Now bxy, byx, this is equal to minus 3 by 2 into minus 1 by 2. So this is equal to 3 by 4, which is less than 1. Hence our assumption is right. Why? Because bxy, byx is equal to r square. And since r square lies between 0 to 1, why r square? If you look at this byx is equal to r into sy sx, bxy equal to r into sx by sy. So therefore, if you byx bxy equal to r into sy sx into r into sx sy, so this is equal to r square. So bxy into byx equal to r square, and since r square lies between 0 to 1, and here we see that this product is less than 1, hence our assumption is correct. Therefore, this is regression equation of, this is a regression equation of, or regression line of y1x, and this is regression line of, or equation of x on y. Okay, I think now it is clear. So please tell me if you have a still problem. Otherwise, I end this thing. Thank you. Thank you, Shashwato, for your queries. So, can I end this stream? Please tell me. So, thank you. Thank you, Shashwato. Thank you. So, okay, we will meet again coming Sunday, same time.